Welcome back to QHSE Talks. Imagine walking onto a sprawling manufacturing floor right now.
Oh yeah, like during peak production hours.
Exactly. It is loud, it's chaotic, and you are the safety professional in charge. And within your first 50 steps, you spot 3 distinct issues.
Just right off the bat.
Right off the bat. First, there's a frayed electrical wire on a multi-million-dollar stamping press.
Yikes.
Yeah. Second, you notice a small puddle of hydraulic oil that's, slowly expanding near the primary loading dock.
A classic slip and fall waiting to happen.
Totally. And third, you watch a veteran forklift driver take a blind corner just a fraction too fast, and he barely misses a structural column.
So a typical Tuesday, basically.
Basically, yeah.
Huh.
Now, here's the harsh reality. You only have the budget, the maintenance personnel, and the organizational capital to fully, permanently fix one of those hazards today.
Just one, which is tough.
It's incredibly tough. Which one do you choose?
Yeah.
Because if you guess wrong, someone gets severely injured or the whole facility goes offline.
And you can't just rely on your gut feeling for that.
No, you absolutely cannot. So today, we are mastering the exact mathematical and philosophical system used to make that choice.
Which is so critical for anyone listening.
It really is, because if you're listening to this, you are likely staring down the barrel of the Associate Safety Professional exam, or, you're a working safety professional looking to sharpen your operational skills.
Or both, honestly.
Right. Today's session of QHSE Talks is an intensive, specialized masterclass geared directly toward conquering ASP Blueprint Domain 2, Topic 4.
Which is formally called Apply Risk Matrix Methodology for Ranking and Mitigation of Risks.
That's a mouthful.
Yeah.
But it is so crucial to place this in the proper context before we even look at a single formula.
It really is. We aren't just reviewing like a footnote in an academic textbook here.
No, not at all.
When you look at the ASP examination blueprint, Domain 2, which covers safety programs and concepts, accounts for a massive 25% of your entire exam.
A quarter of the whole test.
Exactly. You simply cannot pass the test without a mastery of this material.
And even more importantly, beyond the exam environment, this topic represents the lifeblood of the profession, right?
Oh, absolutely. Evaluating controls and determining risks and making worksite assessments easily accounts for, at least 50% of what an associate safety professional actually does day in and day out.
Yeah, safety management certainly involves engineering and regulatory compliance.
But at its absolute core, it is about making highly calculated, defensible decisions in a world that is inherently filled with uncertainties.
It's about the intelligent allocation of fundamentally limited resources, really, to save lives, prevent injuries, and protect the organization's viability.
That framing completely changes how you have to study this.
It really does. And we have pulled together a massive stack of source materials for this session to help you do just that.
We're looking at the official BCSP study guides, the SPAN workbooks,
and Roger L. Brower's foundational text, Safety and Health for Engineers.
plus military safety standards like MIL STD 882E.
And ISO 400-01 implementation guides. We have synthesized all of this into a single, unified, actionable framework.
So you don't need to sift through thousands of pages of slightly varying terminologies.
Because we're going to break down the core methodologies right here, starting with the absolute bedrock.
Right, because across all these diverse sources, from military doctrine to industrial hygiene protocols, there is one fundamental equation.
The big one. Risk equals probability of occurrence multiplied by the severity of outcome.
And you will undoubtedly see variations in the nomenclature depending on the specific standard you're reading.
Like what kind of variations?
Well, sometimes probability is referred to as frequency or likelihood.
Oh, okay.
And sometimes severity is referred to as consequence or impact.
But the underlying math is the same.
The underlying mathematical relationship remains entirely identical. Risk is always the product of how likely an adverse event is to happen and how destructive it will be when it inevitably does happen.
It's basically an attempt to quantify the unknown. I want to ground this for you immediately with a baseline application because the study materials love to test this basic relationship before complicating it.
They sure do. They ease you in.
Yeah. Let's look at a specific quiz question pulled straight from our sources.
Okay, let's hear it.
The question asks, if probability is a 4 on a 1 to 5 scale and severity is a 3 on a 1 to 5 scale, what is the calculated risk level?
Well, the pure arithmetic there is, of course, straightforward. 4 times 3 is 12.
Right.
So the correct answer for the raw score is 12. But this is exactly where many candidates make a fatal error.
Wait, really? How do you mess up 4 times 3?
The math is just the starting point. It's a means to an end, not the end itself.
Oh, I see what you mean. Exactly, because if you just multiply the numbers, write down 12, and walk away, you have done nothing to actually improve the safety of the facility.
Right, you've just completed a third-grade math problem.
A critical insight we pulled from the ASP storage capacity quiz text explicitly addresses this trap, actually.
What does it say?
It states that a safety professional does not just calculate volume, or, in our specific case, just calculate a raw risk number.
Because a computer can do that.
Exactly. The professional must interpret those results, apply the appropriate safety margins based on the environment, and fully understand the operational consequences of those calculations.
And if we look at the My Safety Prep study guide, it notes that these risk ranking schemes provide no absolute quantifiable values.
None at all.
No, they don't constitute a pure quantitative risk assessment by themselves.
So I have to push back on this entire premise then.
Okay, go for it.
If the numbers aren't absolute, like if 12 doesn't equate to exactly 12 units of danger in the real world, isn't this methodology fundamentally just a glorified guessing game dressed up in scientific clothing?
That is a very fair critique, and it's one that engineers often throw at safety professionals.
I can imagine.
It is a subjective exercise, absolutely. But it is a highly structured, systemic, and standardized subjective exercise.
Okay, so it's not totally random.
No, you have to stop thinking of it as a rigid physics equation, like calculating the trajectory of a projectile.
Right.
And start thinking of it as a prioritization engine. It's designed to take the infinite complexity of a work site and filter it down into a manageable hierarchy of action.
So it's really more akin to a weather forecast.
A weather forecast? How so?
Well, if the local meteorologist says there is a 40% chance of rain, that doesn't mean exactly 40 raindrops are going to fall on your head.
True.
And it doesn't mean it will rain for exactly 40% of the day. It is a communicative tool.
Oh, I like that.
Yeah, it takes complex meteorological data and translates it into a format that prompts a human decision like whether or not you need to carry an umbrella when you leave the house.
That is the perfect analogy. The 40% isn't an absolute physical reality you can touch. It is a reliable indicator of future probability designed to alter your current behavior.
Alter your behavior. That's the key.
Exactly. And taking that weather analogy further, the sources introduce a vital concept called risk summation.
Risk summation. What is that exactly?
Well, risk summation is used to aggregate various distinct risks to comprehensively understand the overall risk exposure of a complete facility or process.
Oh, okay.
You aren't just looking at the weather forecast for one specific street corner. You are analyzing the entire regional storm system so the larger organization avoids being blindsided.
That makes a lot of sense. So if I have a chemical mixing station, the risk isn't just the probability of a chemical splash.
No, not at all.
It is the chemical splash plus the risk of the ventilation system failing, plus the ergonomic risk of the operator lifting the heavy chemical drums.
Yes. You have to sum those up to understand the true danger of that one workstation.
Wow, okay.
Precisely. By combining the risk values associated with individual hazards, an overall risk profile can be obtained.
Which is crucial for facility-wide planning.
It is. But to communicate that massive amount of data effectively to people who aren't safety experts, like, say, your plant manager or your board of directors, you need a way to visualize these forecasts.
You need a standardized map.
Exactly.
Which naturally brings us to the visual tool at the heart of this entire blueprint topic, the risk matrix.
Also referred to in several of our sources as the risk measurement matrix.
Right. So how do we take an abstract concept like probability times severity and transform it into a practical daily tool for a safety manager evaluating a production line?
You build a graphical representation. You create a grid.
A grid, okay.
Yeah, standard practice is to place likelihood on your y-axis and consequence or severity on your x-axis.
And then what?
By plotting where a specific hazard falls on both axes, you find its intersection, which dictates its priority.
When you dig into the source materials, you quickly realize there isn't just one universal matrix, though.
No, there are several different flavors of this grid.
The overarching philosophy is identical across all of them, but different industries and standards use remarkably different terminology, scales, and levels of granularity.
That's very true.
And to pass the ASP, you have to be fluent in a few of these dialects.
You do. You can't just know one.
Let's look at the ISO 45001 implementation guide first. This is a globally recognized standard for occupational health and safety management systems.
Right, and they utilize a very specific 5-level likelihood scale.
Yes, and Table 6.2 from the ISO text is incredibly rigid in its definitions.
It really is. It assigns actual hard percentages to its likelihood descriptors.
Which is vital for you to understand because ISO leans heavily into quantitative standardization.
Very heavy. Let's break it down. Level 5 is categorized as almost certain, expected in most circumstances, right?
Right, and they explicitly define that as a 91 to 100% probability of occurrence.
Wow. And level 4 is very likely, will probably occur in most circumstances, sitting at a 61 to 90% probability.
Okay, so a fairly big jump there.
Yeah. Then level 3 is likely, might occur at some time, bridging the 41 to 60% gap.
That's right in the middle.
Exactly. Level 2 is unlikely, could occur at some time, capturing the 10 to 40% range.
And finally, level 1.
Level 1 is very unlikely, may occur only in exceptional circumstances, defined strictly as a 0 to 10% probability.
That structure gives an organization a very rigid, auditable framework.
It really does. If an auditor comes in, you can point to historical incident rates and justify why a hazard is a level 3 versus a level 4 based on actual statistical data.
It's hard to argue with the math.
Exactly. But then you flip over to the military standards, specifically MIL STD 80A2E and the Army's FM 519 on composite risk management, and their approach looks entirely different.
They throw the 1 through 5 numbers out the window, don't they?
They completely do.
Yeah.
The military operates in highly dynamic, inherently dangerous, and often completely unpredictable environments.
So a strict percentage-based system like ISO wouldn't work.
No, it can create a false sense of precision in the fog of war or during a complex tactical training exercise.
So what do they use instead?
Therefore, the military uses descriptive Roman numerals for severity and letters for probability.
Roman numerals. Okay.
For severity, the categories are catastrophic, designated as Roman numeral Y.
Got it. I is catastrophic.
Critical, which is pical, marginal, which is 3, and negligible, which is 4.
So I 3, 4. Catastrophic down to negligible.
And for the probability axis, they utilize frequent as A, likely as B, occasional as C, seldom as D, and unlikely as E.
A through E.
Exactly.
I find it fascinating how the military purposely uses letters and numerals instead of raw numbers.
Why do you think that is?
Well, I think it forces the person doing the assessment to think qualitatively about the hazard rather than just doing mental math.
That's a great point. It stops them from just going, oh, 3 times 3 is 9, we're fine.
Exactly. And to add one more layer of complexity to our review of the matrices, we have the Industrial Hygiene Risk Matrix provided by Flieger in the study text.
Oh yes, the IH matrix.
This one plots an exposure rating of A through E against a hazard class of 1 through 4.
Right, and it's specifically designed to plot task-based exposure against a chemical hazard class.
To determine the necessary health risk follow-up actions like medical surveillance or air sampling.
And while the language shifts from likelihood to exposure rating, the underlying engine is exactly the same.
It's all the same engine.
Whether you are dealing with an ISO audit of a manufacturing plant, a military risk assessment for a live fire exercise, or an industrial hygienist measuring airborne silica dust,
You are fundamentally performing the same task.
you are finding the exact intersection of how bad the outcome is and how often the worker is exposed to it.
Let's talk about the results of those intersections because I noticed a fascinating paradox when I was reviewing the military's risk assessment matrix.
Oh, what kind of paradox?
Let's say you have a catastrophic event, a Roman numeral I. This could be something like a complete structural collapse of a warehouse.
Okay, very bad.
But it is unlikely to happen, category E.
So IE.
Yes, the intersection on the grid is IE. The matrix scores that specific intersection as a high risk.
Makes sense.
But if you take a marginal event, Roman numeral 3, let's say this is a specific piece of sheet metal machinery that frequently gives operators minor, non-life-threatening lacerations.
Ouch. But not lethal.
Right. Because it happens constantly. It is frequent category A.
Okay, so 3A.
The intersection is FIA A. The matrix also scores that as high risk.
Ah, I see what you're getting at.
How can a catastrophic building collapse and a series of minor cuts both be categorized equally as high risk?
That is not a flaw in the matrix. That is its brilliance.
Brilliance. Really?
This raises a fundamental principle about how risk accumulates over time.
Okay, go on.
A catastrophic event, like a facility collapse or a massive chemical release, might be highly unlikely.
Yeah.
But the severity is so extreme potentially resulting in multiple fatalities and the total destruction of the business, that it demands high-level executive attention and significant preventative resources.
Right. You can't just ignore it because it's rare.
Exactly. Conversely, a marginal event, like those minor lacerations, isn't life-threatening in a single instance.
No, it's just a Band-Aid situation.
But if it is happening frequently, the aggregate harm to the workforce is massive.
Oh, I see.
You are dealing with constant first aid treatments, potential infections, massive drops in worker morale, lost productivity, and inevitable regulatory citations.
It adds up.
It really does. The cumulative cost and harm elevate that frequent minor issue to a high-risk priority.
So it's about the aggregate impact over a year, not just one afternoon.
The matrix normalizes these two vastly different types of hazards so that organizational management is forced to address them both effectively.
Rather than ignoring the paper cuts or hyper-focusing only on the explosions.
Exactly. You need a balanced approach.
Okay, so you have this beautifully structured grid. You know your Roman numerals, your ISO percentages, your A through E scales.
You're ready to go.
But how does a safety manager actually find the data to plot a hazard on this grid?
You can't just guess.
Right. You can't just sit in a windowless office, look at a list of machinery, and guess that a hazard is likely to happen. Where does the objective data come from?
It comes from rigorous, deeply systematic, on-the-ground hazard analysis.
Your boot's dirty.
Exactly. The matrix is entirely useless. In fact, it is dangerously misleading if the data fed into it is based on assumptions rather than investigation.
This transitions us directly into the operational core of the safety professional's job. The 11-step hazard and risk assessment process.
Yes, the My Safety Prep study guide lays out these 11 steps explicitly.
And it is essentially the roadmap for your daily duties.
Let's trace a vivid, real-world example through these steps so you can see how this works in practice.
Okay, I like examples.
Let's go back to that veteran forklift driver taking the blind corner too fast near the loading dock. How do we assess this?
All right, step 1.
Step 1 is establish manageable parameters.
Meaning?
You have to draw a distinct boundary around what you are analyzing. We are not analyzing the entire logistics supply chain.
That would take years.
We are analyzing the specific tasks and operation of forklift movement in Sector 4 during peak loading hours. You define the physical space and the time frame.
Step 2 is identify the potential hazards. What is the activity producing the risks?
Right.
In our example, it is the kinetic energy of a 9,000-pound machine moving through an area populated by pedestrians, combined with obstructed lines of sight at the corners.
Perfect. Step 3 is where the heavy analytical lifting begins. Consider failure modes.
This is a massive concept on the exam, isn't it?
It really is. You have to ask, how can this system fail? The forklift brakes could fail.
The driver could become distracted.
A pedestrian could walk outside the designated walkway.
I want to pause on step 3 for a moment, actually.
What's up?
The exam blueprint specifically mentions analytical techniques like FMEA failure modes and effect analysis.
Oh, FMEA, yeah.
How does considering failure modes on a forklift relate to FMEA?
Well, FMEA is a highly structured, historically quantitative method for executing this exact step. It was originally developed in the aerospace industry.
So it's intense.
Very. FMEA evaluates the potential effects from equipment or process failure. What makes FMEA so critical for the exam is that it introduces a third variable to our core equation.
Wait, a third variable? We established that risk equals severity times probability.
Right. But FMEA calculates what is called a risk priority number, or RPN.
RPN. I saw the RPN heavily featured in the SPAN workbook practice questions.
You'll definitely see it.
How does the RPN alter our basic risk equation?
In FMEA, you assign a severity rating based on the potential impact on the end user, usually on a scale of 1 to 10.
Okay, 1 to 10 for severity.
Then you assign a probability rating for the likelihood of occurrence, also 1 to 10.
That's familiar.
But then you assign a detection rating, again from 1 to 10.
Detection.
Yes. This evaluates your system's ability to detect the failure mode before it causes actual harm.
Ah.
The RPN is the product of all three. Severity times probability times detection.
Oh, that's fascinating. So going back to our forklift, let's say the failure mode is a pedestrian walking into the blind intersection.
Okay.
The severity of a strike is very high, maybe an 8 or 9. The probability given the layout is moderately high, maybe a 6.
Sure.
But let's say you install a motion sensor system that flashes bright strobe lights and automatically throttles down the forklift's speed whenever a pedestrian approaches that specific corner.
That's a great control.
Because your ability to detect the failure and intervene is incredibly high, the detection number drops significantly.
Precisely. And because you are multiplying the three numbers, a low detection rating dramatically lowers the overall risk priority number.
It proves mathematically that engineering controls like automated sensors are vastly superior to administrative controls, like just telling the driver to be careful.
Yes. The RPN gives you quantifiable proof that your intervention worked.
That is a brilliant nuance. Okay, returning to our 11 steps.
Right, we were on step 4.
Step 4, determine the frequency and duration of exposure.
So we measure how many times a shift the forklift passes that corner.
Step 5, assess the potential severity or harm.
If a strike occurs, is it a bruised ankle or a fatality?
Step 6, determine the occurrence probability.
Based on historical near-miss reports, how often does a close call happen?
Notice what just happened there.
What?
Steps 5 and 6 are literally gathering the variables needed for your risk matrix.
Yes, exactly. You're building the data. Step 7 is define the risks, which means articulating the specific scenarios based on the data gathered.
And step 8 is the culmination. Rank the risks in priority.
This is where you plot the forklift hazard on your grid alongside the frayed wire and the oil puddle to see which one lands in the darkest red zone.
The final 3 steps pull us out of the analysis phase and into the action phase.
Yes. Step 9, develop remediation proposals.
This involves creating alternate designs or operational changes to achieve an acceptable risk level.
Step 10 is follow-up action to actually implement the proposals.
And step 11 is document the results, which is vital for regulatory compliance and future audits.
When you look at this 11-step process holistically, it guarantees that your use of the risk matrix isn't arbitrary.
It's not just a colorful chart you put in a PowerPoint presentation.
Right. It is the visual output of a rigorous, verifiable, scientific data collection process.
It provides the concrete justification required when you ask management to fund safety interventions.
Which is always the hardest part.
Absolutely. But ranking risks on a matrix inherently means some risks are going to be sitting at the very top of the list in the red zone, and some are going to be at the bottom in the green zone.
That's the whole point of ranking them.
Right. But what actually happens when you, the safety professional, have to walk into the chief financial officer's office and tell management which risks to fix first?
That's a very uncomfortable conversation for a lot of people.
Because we all know the unspoken reality of the job. Fixing hazards costs money. Sometimes it costs a staggering amount of money.
It's never cheap.
How does finance factor into this highly scientific assessment? If you walk in and just say, we have to fix this because it's a level 5 risk, the CFO is going to ask, how much will it cost and what is the return on that investment?
This specific intersection of safety and finance is where many safety professionals historically struggle.
They don't teach you that in biology class.
Exactly. But it is an absolutely essential competency tested heavily on the ASP exam. You have to understand that safety management is fundamentally a resource allocation problem.
Roger L. Brower beautifully conceptualizes this in his text, Safety and Health for Engineers.
He does, yeah.
He introduces a concept called the hazard totem pole.
The totem pole.
Brower essentially takes our two-dimensional risk matrix severity and probability and adds a crucial third dimension, cost to correct.
And when you add this third dimension, you are suddenly creating a much more realistic, accurate model of actual corporate decision-making.
You're speaking their language.
You are no longer just looking at physics and biology, you are looking at economics.
I picture this like performing triage in a hospital emergency room, but doing it while strictly adhering to a municipal budget constraint.
That's a grim but accurate way to put it.
You absolutely want to save everyone and fix every hazard, but you only have so many resources.
Right. Brower explains that you look for the highest combination. He uses the letters A, J, R.
A, J, R. What do those stand for?
They represent a hazard with high severity consequences, high probability of occurrence, and a low cost to implement.
Ah, that is the golden ticket for a safety manager.
It really is. Yeah. You can fix a major, frequent problem, and you can do it cheaply.
On the flip side, the lowest priority on the totem pole is what he categorizes as DMU.
DMU. So that would be...
This represents a hazard with low severity, low probability of occurrence, and a high cost to correct.
Gotcha.
Imagine an incredibly rare scenario where a specific piece of specialized, seldom-used equipment might cause a minor pinch hazard, but re-engineering the machine would cost $3 million.
Yeah, good luck getting that approved.
You are simply not going to get approval to spend millions of dollars to fix a hazard that almost never happens and wouldn't severely hurt anyone, even if it did.
Right. But how do we actually calculate this financial risk? It can't just be vague terms like high, medium, and low when you were dealing with corporate budgets.
Brower's text provides a rigorous mathematical approach to this. He talks about creating a risk index.
Yes, the risk index is a quantitative tool calculated by evaluating a hazard score and a control score for a given department or process.
And the text states that you subtract the hazard score from the control score.
The hazard score is generated using standardized checklists and weighting factors based on the inherent dangers of the process.
Okay, so it measures how dangerous it is naturally.
Right. And the control score is generated by evaluating the effectiveness of the applicable controls currently in place.
So the equation is risk index equals control score minus hazard score.
Exactly. And that means it can be a positive or negative value, depending on whether your controls are adequate for the hazard.
Okay, but a risk index number alone doesn't mean much to an accountant. To translate that into actual dollars, you have to calculate what Brower calls the composite risk.
Composite risk. That's a big term.
And the text defines composite risk as the product of the composite exposure dollars, meaning the total potential financial loss if an accident occurs, and the percentage risk index.
That equation provides the economic value of the relative risk for a specific department.
It is incredibly powerful because it allows executive management to rank all departments relative to each other based on these composite dollar scores.
And strategically apply their limited capital funds for the absolute greatest overall risk reduction.
Which leads us directly into the concept of return on investment, or ROI.
The study guides emphasize over and over that ROI calculations are incredibly useful for safety interventions.
They're the language you use to justify the cost of risk mitigation to stakeholders who might not know the first thing about safety engineering,
but who intimately understand finance.
There is a fantastic question from the Bowen EHS CSP Exam Practice Problems Volume 3 that perfectly illustrates this dynamic.
Let's hear it.
It's question 18, it states. The Chief Financial Officer of XYZ Corporation expects a 10% annual return on investment for all capital projects.
Okay, 10% return.
What is the maximum cost that will be approved for a project that is expected to save $8,000 per year over 10 years? Assume the project will be fully depreciated in the 10 years.
Now, we are not going to read out complex algebraic formulas over audio because no one can visualize that.
No, that would be terrible radio.
But we have to explain the concept behind the math. This is a classic engineering economy problem testing your understanding of the time value of money.
The time value of money.
Yes, you are trying to find the present value of an annuity.
Okay, break that down for us.
The proposed safety project, maybe it's an automated ventilation system that reduces illness, saves the company $8,000 a year for 10 years.
So 10 years of savings.
But because money today is inherently worth more than money tomorrow due to inflation, and that required 10% return the CFO demands, you cannot just do simple multiplication.
Right. If you just did $8,000 times 10 years, you'd get $80,000. That is option C on the multiple choice quiz, and it is a massive intentional trap.
It is absolutely a trap designed to catch people who don't understand financial principles. To solve this, you have to find the discount factor.
The discount factor, how do we find that on the exam?
The ASP exam will typically provide you with financial tables, or you will use the built-in functions on your BCSP approved calculator.
Okay, so you don't have to memorize the tables.
No, thankfully.
Yeah.
The discount factor accounts for that 10% interest rate over the 10-year period.
So instead of multiplying $8,000 by 10, we find that the discount factor for 10% over 10 years is approximately 6.14.
Exactly. You multiply that factor by the annual savings of $8,000. So 8,000 times 6.14 equals roughly $49,156.
Which perfectly matches option B in the Bowen quiz.
So what does that number actually mean for you as the safety manager?
It means you now have a hard, defensible budget cap.
Exactly.
If you can implement that ventilation system for $45,000, the CFO will approve it immediately because you have proven mathematically that it exceeds their required 10% return on investment.
But if the system costs $60,000, it gets denied.
Regardless of where it sits on the risk matrix, unless you can find a way to lower the implementation cost.
Understanding this transforms the safety professional from someone who just complains about hazards and asks for handouts into a strategic, highly effective financial partner in the organization.
You learn how to speak the language of the boardroom.
Exactly.
So, assuming we have successfully secured the funding, we know what needs fixing, we have ranked it on the matrix, and we have justified the budget.
The trifecta.
What actual practical strategies do we use to mitigate these ranked risks?
The ultimate overarching goal of all these strategies, as stated continuously in the exam prep materials, is to reduce risks to LRA.
ALARA.
Mhm.
That stands for as low as reasonably achievable.
And how do we get a hazard down to LRR? We use the hierarchy of controls.
But the sources for this specific blueprint topic provide a system safety approach priority list that is slightly different from the standard NOSH hierarchy you might have memorized in your earlier studies.
Yes, according to the Safety Professional Handbook excerpts, the order of priority for identifying alternatives and reducing risk in system safety is distinct.
Okay, what's priority number 1?
Priority number 1 is to design safety into the system. This means eliminating the hazard entirely through engineering and architectural design before the system is even built.
So fixing it on paper.
Right. Priority number 2 is to use safety devices. This means installing hard barriers, interlocks, or machine guards that physically prevent the hazard from reaching the worker.
Like putting a cage around a saw blade.
Exactly. Priority number 3 is to provide warning devices. Think of alarms, flashing lights, or gauges that alert the worker to a dangerous condition.
Okay, and the last one.
And finally, priority number 4 is to use procedures and training to reduce risk. This is the weakest control, relying on human behavior and compliance to avoid the hazard.
Design, devices, warnings, training. That represents the engineering and operational pathway to risk reduction.
It does.
But what about the broader organizational and financial pathways? The My Safety Prep text breaks down overall risk management strategy into 4 fundamental pillars.
These 4 pillars dictate how an organization philosophically handles the risks you've identified on your matrix.
Let's go through them.
The first pillar is avoidance.
Avoidance is straightforward. You simply do not engage in the activity at all.
Right. If a specific chemical manufacturing process is deemed too dangerous and the controls are too expensive, the company decides to just stop producing that chemical.
You avoid the risk entirely by walking away from the operation.
The second pillar is transfer. This involves shifting the financial burden of the risk to another entity.
Oh, like a quiz question I saw. It specifically tests this concept, stating that risk transfer is a technique which shifts financial risk from one party to another.
The most universal example of this is purchasing insurance.
Right. If the cost of a massive, comprehensive fire suppression system for a remote storage warehouse is $5 million, but the probability of fire is incredibly low, the company might choose to pay a $50,000 annual insurance premium instead.
They transfer the financial devastation of a fire to the insurance underwriter.
The third pillar is mitigation, or loss control.
This is the traditional domain of the safety professional. It involves proactively reducing the possibility that a loss will occur and simultaneously reducing the severity of those incidents that do occur.
This is where your hierarchy of controls, the guards, the training, the sensors is actively deployed.
Exactly. And the fourth pillar is financing, also known as retention.
Retention, what does that mean?
This involves the company accepting the risk and keeping it in-house. They might create a dedicated reserve fund to pay for potential damages out of pocket.
Okay, but what is truly fascinating here, and something that catches a lot of safety professionals off guard, is that the text explicitly states another option under this category.
Intentionally choosing to spend nothing.
Wait, spend nothing is an official safety strategy.
It sounds deeply counterintuitive to the entire ethos of safety, but Brower's text confirms this is a valid strategy.
That's wild.
Choosing to spend nothing is a calculated official organizational decision to take a chance that a risk event will simply not occur, or that if it does, the cost is acceptable.
And crucially, it's a decision based directly on the intersection of the risk matrix and the cost-benefit analysis we discussed earlier.
Exactly. It comes down to a concept called risk tolerance. Every organization has a different appetite for risk.
Give me an example.
Well, a heavily regulated nuclear power plant has an incredibly low risk tolerance. They will spend millions to mitigate highly unlikely events.
Makes sense.
But a fast-paced, disruptive tech startup manufacturing consumer goods might have a much higher risk tolerance. They will choose to implement less stringent strategies and retain more operational risk to move faster.
So this goes right back to the DMU hazard on the totem pole. If an event has low severity, a remarkably low probability, and an astronomical cost to fix, the objectively correct business management decision might be to retain that risk, implement zero controls, and literally spend nothing.
Exactly. The safety professional's job is not to force a zero-risk environment, because that is economically impossible, but to accurately and objectively present the risk matrix and the financial data, so executive leadership can make an informed, defensible choice based on their specific tolerance level.
This has been an incredibly deep exploration of the material.
It really has. We covered a ton of ground.
Let's bring all these threads together to summarize exactly why you need to know this.
Well, Domain 2, Topic 4, demands that you understand not just how to multiply two numbers on a grid, but how that mathematical exercise feeds into massive global safety management systems.
The blueprint explicitly mentions frameworks like ISO 4501 and ANSIZ 10.0. These standards require a systematic, documented approach to risk.
Right. We started on the warehouse floor, identifying hazards through rigorous field observation and techniques like FMEA.
We took the variables of probability and severity and plotted them on a structured matrix, whether that was a strict 5x5 percentage grid like ISO or the military's Roman numeral system designed for dynamic environments.
We ranked those risks, so we knew what to attack first.
We factored in the cold, hard financial cost to correct them, using tools like the hazard totem pole and time value of money ROI calculations so we could actually get the budget approved.
And finally, we applied the hierarchy of controls and the 4 pillars of risk management avoidance, transfer, mitigation, and retention to systematically reduce that risk down to ALRI.
While passing the ASP exam is the immediate pressing hurdle you are facing, you must always remember the ultimate objective.
The goal is preventing catastrophic accidents.
It is ensuring that the human beings on that manufacturing floor go home to their families in the exact same condition they arrived.
The texts emphasize systems theory, which requires a holistic perspective. You have to understand how a simple 4x4 colored grid on your computer screen directly connects to corporate budgeting, to employee training, to the company's culture, and to physical reality.
It is a massive responsibility, but armed with these structured methodologies, it is a completely manageable one. You are no longer guessing. You are engineering safety.
That's well said.
Thank you for joining this exhaustive session of QHSE Talks. We have broken down the math, the matrices, and the money behind professional safety management.
But before we sign off, I want to leave you with an important question to ponder as you continue your career.
Oh, a closing thought. Let's hear it.
We have established today that risk matrices, despite their rigid numbers and complex grids, are ultimately subjective tools. Their output is heavily influenced by an organization's specific internal risk tolerance.
Right.
If the math of a risk matrix inherently changes depending on whether a company is flush with cash or struggling with its budget, how do you, as an individual safety professional, maintain your own objective standard for what constitutes a truly safe working environment when you inevitably move from one organization to the next?